Welcome to This Explainer. Today, we're diving into a highly detailed, no-nonsense engineering mentorship session, and we're targeting this specifically at EPC piping and process engineers. We're going to tackle a topic that, honestly, looks incredibly simple when you're just reading about it in a textbook, but out in the real world, it causes real confusion and sometimes catastrophic incidents when engineers don't understand the fundamental why behind it. We're talking about spec breaks around control valves. I want you to imagine I'm a lead process engineer sitting right next to you. We've got a complex unit P&ID spread out on the table between us, and we are going to walk through exactly how to assign piping classes safely, strictly following code, and economically for the project. Let's get into it. So here's our roadmap for this training module. First, understanding the spec break. Second, operating versus design pressure. Third, the control valve misconception. Fourth, evaluating maximum credible pressure. Fifth, real engineering project examples. And finally, a quick spec break checklist. Section 1. Understanding the spec break. We are establishing the baseline of what actually occurs on the pipeline. Before we jump into a real-world sizing scenario or a relief calculation, I want to pose a really fundamental question to challenge your baseline understanding of those little lines on your drawings. What really changes when we cross a spec break line on a P&ID? Is it just some paperwork formality for the piping material control team? Or are we fundamentally altering the physical reality of the plant's pressure containment capability? Think about the physical hardware transition happening in the field. How does a system step down from a 52-bar Class 600 upstream source to a 19-bar Class 300 downstream limit safely? You see, a spec break is a literal, physical change in piping specification, not merely a change in operating pressure. On the upstream side, you might have a design pressure of 52 bar and 120 degrees Celsius, built to Class 600 specifications. Think about the physical hardware required for that kind of containment. We're talking thicker schedule pipe, heavy-duty flanges, high-tensile bolting. Then you hit the control valve, and right after it, there's that spec break. Suddenly, on the downstream side, the design rating drops to 19 bar and 80 degrees Celsius, moving down to a Class 300 specification. You're transitioning to thinner wall pipe and lighter flanges. This is absolutely crucial to grasp as a process engineer. From this precise point onward, the pipe, the flanges, the valves, the fittings, the gaskets, literally the bolting, all of it is built to a completely different, lower pressure temperature capability than the system feeding it. To really anchor this concept, and honestly, this is a great mental model to use when you're training junior team members, think of a complex piping system exactly like a highway system. Different sections of a highway are built for entirely different traffic loads and speeds, right? A quiet village road is simply not engineered, graded, or constructed like a massive national highway, even though the exact same cars have the ability to drive on both of them. In our process plants, it is the exact same fluid flowing through the pipe, but the different sections are engineered for vastly different pressure and temperature capabilities. So you might be wondering, what are the project-level driving forces for introducing these spec breaks in the first place? Why not just build the whole plant to the maximum pressure rating, like a massive national highway everywhere, and eliminate the risk entirely? Well, first, EPC cost optimization. If you design your entire downstream piping to match the upstream high-pressure source, you are buying heavier schedule pipe, higher rated flanges, and much more expensive manual valves for potentially thousands of meters of piping. Throw in exotic metallurgy like duplex or Inconel, and the costs absolutely skyrocket. Second is practicality. You simply cannot gold plate every single line in a multi-billion-dollar process plant. The project economics would just collapse. Third, it reflects the true code intent for pressure design. The pipe class should mathematically match the pressure it will actually experience under worst-case credible scenarios, not the absolute highest pressure anywhere in the entire facility. But listen closely to this trade-off. A spec break is only free money if it is placed correctly. Downgrading downstream piping saves significant capital cost, sure, but incorrect placement creates a catastrophic weak link in your system that can literally rupture under pressure. Section 2. Operating vs. design pressure. This is our process safety baseline. We need to deliberately contrast operating pressure with design pressure. Now, while this might seem elementary, confusing these two parameters trips up a lot of fresh engineering graduates during their very first P&ID reviews. Think of it like automotive capability. Operating pressure is like your normal driving speed. It's the steady state, what the system runs at day to day. It's the standard value you see on the DCS control screen on a normal Tuesday afternoon. Contrast that with design pressure, which is your maximum car capability. If you normally drive at 80 kilometers per hour, you don't buy a car that maxes out and rattles apart at 81 kilometers per hour. You buy one rated from much higher speeds because traffic fluctuations, downhill slopes, and sudden emergencies happen. Your piping is exactly the same. It experiences thermal expansion, surge pressures, and process upsets. Let's lock in the strict technical definition required by piping codes. Design pressure is the maximum internal pressure the equipment or piping is built to safely withstand. And importantly, this includes a robust, calculated margin above normal continuous operation to account for upsets, control deviations, and abnormal situations without failing. Why does this exact definition matter so much for spec breaks? Because when you size downstream piping, you must absolutely never size it for the operating pressure alone. Never. Downstream piping must be evaluated and sized for the absolute worst credible pressure it could see during a failure. That worst credible pressure subsequently dictates the new design pressure for that specific downstream pipe segment. Section 3, the control valve misconception. Honestly, this represents the most dangerous error junior engineers make. There's a really common quote you hear in the design office, and it usually sounds something exactly like this. Great, downstream operates at 10 bar, so I'll just spec the downstream piping for 10 bar, add a 10% margin, and call it a day. If you're an engineer thinking this way, assuming the normal steady-state modulating outlet pressure naturally dictates the downstream piping class, you are falling into a massive process safety trap. A control valve dropping pressure from 40 bar to 10 bar in normal operation is just a momentary snapshot of an intentional, dynamically controlled condition. It totally relies on instruments working perfectly. That operating pressure tells you absolutely nothing about what happens when that dynamic control is lost. We really need to thoroughly analyze the mechanical realities of control valves. They are not magic pressure walls. They are physical mechanical devices with moving parts, stems, plugs, seats, actuators, and they do not always sit exactly where you command them to. First, evaluate the valve failing in the open position. Whether it's an air fail open design losing instrument air, an actuator diaphragm rupture, or simply a mechanical sticking of the stem due to debris in the line, the result is exactly the same. Downstream pressure will rapidly rise toward the full upstream pressure with almost zero frictional drop. Second, you've got to analyze a control loop malfunction. The valve hardware itself might be totally fine, but a stuck positioner, a drifting pressure transmitter signal, a P&ID controller tuning issue, or even a board operator accidentally forcing the controller output to 100%, all of those can drive that valve wide open mechanically. Third, and highly critical for EPC design, there is almost always a manual block valve bypass installed around the main control valve to allow for maintenance while the plant is still running. If that manual bypass is opened by an operator during startup or during live system maintenance without extremely careful throttling, full upstream pressure shoots straight into your downstream piping completely unrestricted. This perfectly illustrates our core foundational engineering philosophy across all heavy industries. Pressure design must always consider the single credible failure case, not just the intended operating case. This isn't just a best practice guideline. This is precisely what rigorous piping codes, international standards, and maximum process safety principles demand of us. You have to mathematically evaluate the maximum settle out or dynamic pressure the downstream system could be exposed to under any single credible failure, well before deciding where it is safe to step down the piping class on your drawing. Section 4, Evaluating Maximum Credible Downstream Pressure. Let's look at the step-by-step methodology lead engineers actually use in the field. All right, here is the 4-step practical checklist you need to memorize and apply during every single P&ID review. Step 1. Identify the maximum upstream source pressure. What is the absolute highest pressure the upstream system can physically deliver? Do not look at the normal operating upstream pressure. Look at the upstream relief valve set pressure, evaluate the centrifugal pump shutoff head, or find the compressor discharge pressure right at the surge limit. Step 2. List all credible control valve failure modes. We just covered these extensively, right? Failing wide open mechanically, loss of instrument air, or manual bypasses being accidentally opened during commissioning. Step 3. Determine downstream pressure under the worst failure. Conservatively, if flow stops or is severely restricted further downstream, this answer is almost always the full upstream design pressure, simply because there is no continuous flow to create a frictional pressure drop. And step 4. Check for independent downstream overpressure protection. That brings us perfectly to the culmination of this whole methodology, the key decision point. Is there independent overpressure protection? Stepping down the piping class immediately after a control valve is strictly dependent on having an independent protection layer, specifically a properly sized pressure safety valve, a BSV, or another certified independent relief device acting as your safety net. If you have that independent layer of protection actively preventing pressure from exceeding the downstream piping rating, you can safely put the spec brake right after the control valve. If you do not have that protection, well, that downstream piping must be heavily rated to withstand the full upstream design pressure until you route it to a point where protection finally does exist. Expanding on those failure scenarios for your process safety documentation, you've got to always ask and document these specifics. What is the valve's exact fail-safe position on loss of instrument air or electrical signal? Does it fail open, fail close, or fail last position? And more importantly, does that specific fail-safe position itself create the downstream overpressure case? You must also heavily scrutinize manual maintenance bypasses. They exist practically everywhere in real physical plants, and they are a very common root cause of chemical and refining incidents when an operator opens them, completely unaware of the strict downstream piping material limits. Finally, evaluate the block valve isolation philosophy for maintenance versus live operation. Documenting these specific scenarios is a critical part of defining nodes in a wider unit HAZUP, and it's foundational to your relief valve sizing exercise. The exact location of a spec break is a direct engineered output of that rigorous safety study, never, ever a casual drafting assumption. Section 5, Real Engineering Project Examples. Let's take all this theory and look at practical execution. Let's methodically analyze 3 field-style examples to see exactly how this plays out in EPC design. Example 1. We have a utility letdown station, dropping high-pressure steam from 40 bar to 10 bar. Downstream, there is a properly sized PSV set just above the 10 bar design limit, installed directly before the spec breakpoint. The outcome? It is completely safe. The piping is rated for 10 bar class, the spec break is right after the control valve assembly, and if the valve fails mechanically open, the PSV lifts and safely relieves the capacity. This is legitimate, code-compliant, cost-saving design. Now look at example 2. The upstream source is 25 bar. A junior engineer specs the downstream piping for the normal 5 bar outlet without checking for a relief device. Crucially, there is a manual maintenance bypass installed. During plant startup, a field operator opens that manual bypass to establish initial flow and clear the lines. The outcome? A highly dangerous mistake. The thin wall 5 bar piping is suddenly hit with 25 bar of deadhead pressure. It will likely yield or rupture. This is exactly what our design philosophy is meant to prevent. Finally, example 3. Instead of installing a costly new PSV and dealing with the associated flare header piping just to allow an early spec break on a really short pipe run, the lead engineer extends the heavy, higher pressure upstream piping class further downstream. They extend it until it reaches a large separator vessel that naturally limits pressure or connects to an existing relief system. The outcome? A safe, highly practical design compromise that avoids unnecessary maintenance burdens while maintaining total pressure containment. Section 6, Quick Spec Break Checklist. Let's look at an actionable tool you can start using today. Whenever you are reviewing a unit P&ID or assigning piping material classes, apply this strict 6-question working method every single time. Question 1. What is the absolute maximum pressure the upstream source can ever physically deliver? Question 2. What is the valve's mechanical fail-safe action, and is there a manual bypass installed? Question 3. If the control valve fails wide open or the manual bypass is inadvertently opened, what pressure actually reaches the downstream piping system? Question 4. Is there an independent certified relief device actively protecting the piping before that critical pressure is reached? Question 5. Only if the answer is yes, you may confidently place your spec break right after the valve assembly, stepping down to the lower piping class. Question 6. If the answer is no, you must keep the higher, heavier piping class extended downstream until independent protection exists. Build this rigorous habit. Internalize this logic. You will never make the classic spec break too early mistake, and you'll finally understand why your lead engineer meticulously marks up your drawing reviews the way they do. So, I want to leave you with this final provocative thought. Go back to your desks today. Open up your current EPC project P&IDs. Trace the lines from the high-pressure sources and ask yourself, are your plant's piping systems truly protected against a single failure overpressure event at the spec break? Use this rigorous process safety methodology to evaluate your own facility designs. Thank you for joining me in this explainer, and keep engineering safe.